If human decided today that we are going to visit the closest star to Earth, how long do you think it would take? 50 years? 100? Maybe a few centuries? What if I told you that even using the fastest spacecraft we have ever built, it would still take tens of thousands of years to get there? And that star is not across the galaxy. It is our next-door neighbor in space. I am talking about Proxima Centauri. It is only 4.24 light-years away. That sounds close, right? 4.24. It feels small, but that number hides something almost impossible to imagine. Light is the fastest thing in the universe. Nothing with mass can move faster than it. It travels at about 300,000 kilometers every single second. In 1 second, light could circle Earth more than 7 times. In 1 year, it travels about 9.5 trillion kilometers. So when we say 4.2 for light years, we're talking about nearly 40 trillion kilometers. Pause for a second and really think about that. 40 trillion kilometers. Let me make it feel real. Imagine you are driving a car at 100 kilometers per hour. You never stop. No sleep. No refueling breaks. Just driving non-stop toward Proxima Centauri. It would take you more than 45 million years to arrive. That is not an exaggeration. 45 million years. That is longer than humans have even existed as a species. Now you might say, okay, but we would not drive. We have rockets. We have advanced technology. Fair point. So let us look at our fastest spacecraft ever created. The Parker Solar Probe can reach speeds of over 700,000 kilometers per hour when it gets close to the sun. That is unbelievably fast by our standards. But even at that speed, reaching Proxima Centauri would still take thousands of years. Voyager 1, which has been traveling since 1977 and is now in interstellar space, moves at around 61,000 kilometers per hour. At that speed, the journey would take more than 70,000 years. That means, if it had been launched during the time of the first pyramids, it still would not be anywhere close today. So, here is where things get serious. If we want to reach another star within a human lifetime, we would need to travel at a significant fraction of the speed of light. Maybe 10%, maybe 20%. And this is where physics becomes brutally honest. There is something called the rocket equation. Delta V equals exhaust velocity, multiplied by the natural logarithm of the initial mass, divided by the final mass. You do not need to memorize it. The simple idea is this: the faster you want to go, the more fuel you need. But not just a little more, exponentially more. Fuel as mass. More fuel makes your spacecraft heavier. A heavier spacecraft needs even more fuel to accelerate. It quickly becomes impossible. Even if we tried to push a spacecraft to just 10% of light speed using traditional rockets, more than 99% of the total mass would have to be fuel. And that still might not be enough. And then there is the ultimate limit. According to relativity, as you get closer to the speed of light, the energy required to accelerate increases dramatically. E is equals to mc squared. The closer you get, the more extreme the energy demand becomes. Eventually, it approaches infinity. In simple words, reaching light speed with a spacecraft that has mass is impossible. Even if we tried to push a spacecraft to just 10% of light speed using traditional rockets, more than 99% of the total mass would have to be fuel, and that still might not be enough. And then there is the ultimate limit. According to relativity, as you get closer to the speed of light, the energy required to accelerate increases dramatically. E is equals to mc squared. The closer you get, the more extreme the energy demand becomes. Eventually, it approaches infinity. In simple words, reaching light speed with a spacecraft that has mass is impossible. But let us say for a moment that somehow we solve propulsion. We find a breakthrough technology. We manage to travel at 15% of light speed. The trip would still take decades. Now imagine being on that spacecraft. You leave Earth in your 20s. You might arrive in your 60s. Life support systems would need to work perfectly for half a century. Water would have to be recycled over and over without failure. Food would need to be grown or preserved reliably. Oxygen systems could not afford a serious malfunction. Then there is radiation. On Earth, we are protected by a magnetic field. In deep space, there is no such shield. Cosmic radiation would constantly hit the spacecraft. Over decades, That exposure could seriously impact both electronics and human health. And here's something that sounds small, but is actually terrifying. Interstellar space is not completely empty. There are tiny particles, microscopic grains of dust. At speeds of 10 or 20% of light speed, even a tiny speck could hit with enormous force. A collision with something the size of sand could release energy comparable to an explosive blast. Now imagine this scenario. You are 25 years into the mission. Something critical breaks. You send a message back to Earth asking for help. That message takes over 4 years to arrive. The reply takes another 4 years to come back. That is 8 years just for one conversation. You are truly on your own. This is why Proxima Centauri, despite being our closest stellar neighbor, remains completely out of reach for now. It is not just about distance. It is about speed. It is about energy. It is about the fundamental laws of the universe. And this is only the beginning of the story, because next, we need to talk about nuclear propulsion, generation ships, and whether humanity could ever realistically attempt something like this. Once you understand those challenges, you will see Proxima Centauri in a completely different way. Stay with me, because what comes next will make you realize just how enormous and unforgiving the universe truly is.